Okay, guys, this is just another video and it's explaining the same practice quiz that we went over in class today, and it's the same practice quiz that I already have a video on that I've already posted, but I just wanted to go over a couple more things, just add a couple more things to it. So this is just a video lesson. So this is titration lab quiz number two, practice quiz number two. So you have your titration lab quiz coming up. It is going to be very similar to the practice quiz we're about to go through. So the one that we just did in class after our redox titration lab, our hydrogen peroxide lab, we went over practice quiz number two. And this video covers practice quiz number two. And this is going to be very similar to the quiz you're going to take in class next time. Okay, now I already have a video posted covering it, but this one might have a couple more extra details in there to maybe hopefully clear things up. So, but if you already watched the other video and you get it, or you understand what we went over in class today, then you should be in good shape. All right, so let's dive into it. Okay, so again, here is the first question. So you're gonna on the titration quiz, you're going to have one acid-base titration question, and you're going to have one redox titration question. Okay, so remember we did an acid-base reduction, an acid-base titration lab, and we also did a redox titration lab. So we've done the labs, we've done practice with it. So hopefully you get it. All right, but let's go into this. All right, so first question, we want to determine the molarity of a hydrocyanic acid solution. Okay, so we take 12 milliliters of that solution and we're going to analyze it by titrating it with sodium hydroxide. Now the molarity of sodium hydroxide is 0.025 molar. Okay, so if we're visualizing what we're doing, okay, right, we have HCN, hydrocyanic acid. We got a big old tub of it, but we don't know its molarity, right? That's what we're trying to figure out. Okay, so what do? We take a little bit of this. We just take a little bit of this, but we measure the volume that we take. So we take 12 milliliters. Why not 10? I don't know. The question just said we took 12 milliliters. So we took 12 milliliters of this big old vat of HCN. So we took a little tiny bit of it, 12 milliliters. And what we're going to do is analyze that 12 milliliters. And if we can figure out how many moles of HCN are in that 12 milliliters, moles divided by 0.012 liters would give us the molarity of that HCN solution that we have a big old vat of. And now we could use that HCN to do whatever with, okay? And since we know its concentration now, we're good to go, right? So that's the whole goal. Figure out the molarity of this, right? So if we're doing a titration, that 12 milliliters of HCN that we measured out goes in the flask. We'd also want to put an indicator. So I know the question said we used phenolphthalein as our indicator, okay? And then what we would do is from our burette, slowly add the NaOH to the 12 milliliters of HCN until we reach the end point of the titration, right? And we would know that when the color changes. So in this scenario, when it turns from clear to pink, that's when we've reached the end point of our titration, okay? So that's the whole idea, all right? That's the whole idea, all right? So then once we know the volume of the NaOH solution, since we already know its molarity, we could figure out the moles of NaOH. It reacts with HCN in a 1-to-1 ratio, so then we could figure out how many moles of HCN we have. And then to figure out the molarity of that HCN solution, we would take the moles of the HCN and divide it by the volume, but make sure you divide it by liters, not milliliters. And that would give us our molarity, and that's it. That's what we would do, all right? So a couple questions that we're gonna ask about this is, first, the first part of this question is just, hey, what's the net ionic equation? Okay, so the thing we have to know about this acid-base titration is this is a weak acid being titrated by a strong base. And whenever that's the case, this is kind of how your net ionic equation is going to look. So when you have a weak acid, strong base, we can call a weak monoprotic acid HA, H plus, one H plus paired up with an anion, A, okay? And so if this is H plus, then A is A minus, but when they're together, right, just like an ionic compound, we don't write the charge, okay? And now because it's weak, we don't dissociate it in our equation. So I keep this as HA, okay? Now the sodium is going to end up canceling out as a spectator ion, so all we have is hydroxide. We always get water, and then we're left with A minus. So this is how our model of a weak acid, strong base, net ionic equation will always look. So to apply this model to the reaction that we were doing in the question, cyanide is our anion. So here is our net ionic equation for the reaction that's going on. Okay. Understand that if this had been a strong acid instead, like HCl or HNO3 or something like that, then this is the net ionic equation. An H plus plus an OH minus yields water. But when it's weak and strong, this is what it's going to look like. All right, right here. Okay. All right. So that's our net ionic equation. Okay. To figure out the volume of NaOH to reach the equivalence point, we got to do final minus initial volume. You know, technically we should start at 0, but you know, they're never going to start at 0 in a free response problem. So what did the person do? They filled up the burette to 2.51 milliliters. That's where they started the titration, and they slowly added the NaOH until we went from clear to pink, and the final volume reached is 28.84 milliliters. So if I just do final minus initial, that's how many milliliters of NaOH were required. Now remember, because this was a 1-to-1 acid-base ratio, because we have one H plus and one OH minus, we could do our shortcut to answer this question, calculating the molarity of the HCN. So we could do MAVA equals MBVB. So VA would be 12 milliliters. Molarity of the base is 0.025, and the volume of the base is what we calculated here, 26.33. So we could just solve for molarity of the acid. Now the stoichiometric way would be to take our volume of NaOH times the molarity of NaOH. That gives us moles of OH minus. It's a 1-to-1 ratio from our balanced equation, right? And that would give us moles of HCN. And then we would take that many moles of HCN and we divide it by the volume of the original HCN sample, which was 12 milliliters, but for molarity, we need to divide by liters, so that's 0.012 liters, and we get our molarity of HCN. So boom, we got our molarity, okay? Now, some other questions they're asking to calculate the pH of that NaOH solution. So this is just kind of a one-off question. This really doesn't have anything to do with the titration portion. It's just, hey, what's the pH? So remember, we got to know some pH stuff. All right, so I know we're not going to really focus on acid-base chemistry in depth until we get to Unit 5, but these are equations we learned in Chemistry 1. Okay, so we should know that if I want to calculate pH, I need to know the H plus concentration, so the negative log of that would give me the pH. The POH is equal to the negative log of the OH minus concentration, the hydroxide concentration. But how do they tie together? pH plus POH always equals 14. So in this question, we know the molarity of hydroxide because we know the molarity of sodium hydroxide, and we know that this is an aqueous ionic compound, so it is dissociated 100%. That's what aqueous ionic is. So for every one NaOH, there's one OH minus. So this molarity is the molarity of hydroxide. So if I take the negative log of that molarity, that's going to give me the POH, and then all I have to do is subtract from 14 to get the pH. Okay, so that's what we do over here. So I take the negative log to get the pH, and then so 14, this is wrong, 14 minus the POH would give us the pH. So it's not the POH minus 14, it should be 14 minus. And so we get the pH equals 12.4, okay, of that NaOH solution we were using. Okay, remember we use phenolphthalein because phenolphthalein changes color at a pH of 8, and we should always understand that when we have a weak acid, strong base combo, the pH at the end point of the titration is always going to be above 7. So you want an indicator that changes color above 7, and that's why phenolphthalein is used. Okay. We'll learn in Unit 5 how we could calculate the pH of the HCN solution, but we can't calculate the pH of the HCN solution, even though we know the molarity. We know the molarity of the HCN solution. And if it had been HCl, this molarity would be the molarity of the H plus, and I could take the negative log of that to get the pH. But because HCN is weak, it doesn't completely dissociate. So yeah, we know the molarity of HCN, but we don't know the molarity of H plus. We know that the molarity of H plus is going to be less than this, less than what we calculated, because it doesn't completely dissociate, but we don't know what it is. We'd have to know more information. And we'll learn how to do that in Unit 5. Okay? What would the titration curve look like? Right? You get your normal kind of S titration curve, but that equivalence point, the point of inflection, would be above a pH of 7. All right? All right. The main thing is to understand what's going on with this titration, right? Understand that calculation, understand that calculation. And yeah, I do want you to know your pHs and pOHs and that kind of thing. But also knowing the net ionic equation. That's part of this unit, and you need to know that. All right. So let's go to our redox titration question. Okay. So here we have iodine, right? But it's contaminated with inert impurities. So it's not just pure iodine. I don't just have a sample of pure iodine. I have this sample of solid iodine, and sprinkled in it is some other stuff that's not iodine. But the cool thing about these impurities is we're told they don't react, okay? So what we're going to do is we're going to take a 15-gram sample of this iodine, which also contains impurities. So the 15 grams is not iodine. A lot of it's iodine, but some of this 15 grams is whatever the inert impurities are, okay? So you don't have 15 grams of iodine. You have 15 grams of an iodine sample that also contains other things. All right. And so what we're going to do is titrate it with hypochlorite ions. We don't care about the sodium. The sodium is just our source of the hypochlorite ions, okay? So this is the reaction that's going to be taking place, okay? So we're going to have to balance that reaction and all that stuff. But what we're going to do is, and it's really not titrating it, what we're doing, we're just going to flood this with an excess of oxalic acid so that all of the iodine in that 15-gram sample will react. Okay, that's kind of the idea. So let's visualize this, okay? So we have this big old container of iodine, but we know it's not just iodine, there's some other things in there, okay? So we want to figure out, well, what percent by mass of this is actual iodine and what percent is inert impurities. So we're going to take a small amount of it. We're going to measure out a mass of this solid that we can analyze. So we measure out 15 grams of it, okay? And then what we do is we react it with an excess of the hypochlorite ion so that all of the iodine that's in that 15 grams will react. We don't know, maybe it's 14.5 grams, maybe it's 13 grams, maybe it's 13.98 grams, maybe it's 14.99 grams, maybe it's only 2 grams, maybe it's a lot of inert impurities. We don't know. That's what we're trying to figure out. So what we're trying to do is figure out how much of this 15 grams is actual iodine, right? That's the whole goal. So we're going to completely take this and react it with the hypochlorite ion, knowing that when the reaction stops, it's because we ran out of iodine, okay? All right, and so the reaction that's taking place is this one, all right? This is the balanced equation. If you want to review, you can go back and review the other videos to show how to balance this in an acidic solution. Okay, that's fine. The key for the rest of this question is figuring out this ratio. 5 moles of chloride are produced for every 1 mole of iodine that reacts, okay? But anyway, what we're doing is flooding this sample of iodine with an excess of hypochlorite ions, so this reaction goes to completion, and it only stops when we run out of iodine, right? That's the idea, okay? All right, so here's our balanced equation. All right, so then our whole goal, remember, our whole goal is to figure out how much iodine reacted. Because if we can figure out how much iodine reacted in terms of grams, that would be how many grams of iodine we have in that 15-gram sample, so then we can determine the percent by mass, right? Okay. So this wasn't implied in the practice problem, but you'd have to do it because remember, what's in the beaker after this reaction goes to completion? Okay, well, we know iodine's limiting. So after this reaction goes to completion, there's no more solid iodine, right? Now, this was in excess, so we're still going to have some hypochlorite ions still in there. And then we have all of these ions. So we're going to have a bunch of H+, we're going to have a bunch of chloride, we're going to have a bunch of iodate ions. But then we would also have some of those solid impurities that didn't react from this 15 grams. So what you would do is filter the resulting solution to get all the impurities away. And then what would be left over, okay, is now you have nothing but stuff dissolved in water. And the stuff that's dissolved in water would be the iodate ions that were produced from this reaction, right? The chloride ions that were produced by this reaction, the H+ ions that were produced by this reaction, and then you would have any leftover hypochlorite ions because that was your excess reactant. Remember, no more solid iodine because all of it reacted, and we filtered out all the impurities, okay? So now our goal is to figure out how much iodine reacted, okay, based on what's over here, okay, based on what was produced. So we got three things that were produced, all right? So if I could figure out how much iodate was produced, I could multiply by 1/2, and that would give me moles of iodine that were produced. If I could figure out how many moles of chloride that were produced, times 1/5 would give me how many moles of iodine reacted, right? If I could figure out how many moles of H+ were produced, times 1/2 would give me how many moles of iodine reacted, right? That's our whole goal. So let's see what the student did, right? So what the student did was take that resulting solution and flood it with lead nitrate. And they know that the lead ions are going to react with the chloride ions to precipitate lead 2 chloride. So what they did was they took this solution and they flooded it with Pb2+, okay? We don't care about the nitrate, it's a spectator ion. Just like we didn't care about the sodium from the sodium hypochlorite. We don't care about that, all right? Spectator ion. So again, our goal is to figure out the iodine. So to figure this out, the student flooded the resulting solution with excess lead 2+, knowing that any chloride that's in the solution is going to precipitate with lead and form a solid. So for every 1 lead that I add, 2 chlorides will precipitate, and I'll get lead 2 chloride. Okay. And then what did they do? They filtered the precipitate and found the mass of the precipitate. So they found that 28.98 grams of lead chloride precipitated. Now we can take that and figure out how many moles of chloride are in this many grams of lead 2 chloride. But all of that chloride that's in the lead 2 chloride was produced by this reaction. So the moles of chloride in here are equal to the moles of chloride that were produced from this equation. So then if I take that moles of chloride and I multiply it by 1/5, that would tell me how many moles of iodine reacted. And then times the molar mass of iodine would give me how many grams of iodine reacted. And that would be how many grams of iodine were in the original 15-gram sample. Okay? All right. So we're going to take the amount of lead chloride produced to figure out how many moles of chloride were in that precipitate. Then the moles of chloride times the mole ratio of iodine to chloride from our balanced redox reaction would give me how many moles of iodine reacted. Times the molar mass of iodine would give me the mass of iodine in our 15-gram sample. And so the percent iodine by mass would be that mass of iodine divided by the 15 grams, the total mass, times 100. Okay? So let's see what we did here. So to figure out moles of chloride, I take the mass of the precipitate divided by the molar mass. They gave me that. That gives me moles of PbCl2. But I'd have to recognize that there's 2 chlorides for every 1 mole of PbCl2. So I got to multiply by 2 here. So that's how many moles of chloride precipitated. Now, all of that chloride came from this reaction. So now we're going to take that moles of chloride, multiply it by 1/5, and that'll tell us how many moles of iodine reacted, okay? So I take my moles of chloride produced from the redox reaction that happened to be in the precipitate, right? Times 1 over 5 gives us moles of iodine times the molar mass of iodine. And again, they gave us that, but I2, you just go to your periodic table and calculate the mass of two I's, right? That'll give us grams. So that would be grams in that 15-gram sample divided by the 15-gram sample times 100. That gives us our percent by mass. Okay? So if we go back to kind of our visualization, now we know that in our iodine solid sample, only 70%, 70.5% of this is iodine. So about 29.5% is inert impurities. Okay? So we don't have a very pure sample of iodine, right? It's only 70%, right? So that's what we determined through this laboratory process. Okay? All right. So I know we went through this practice problem pretty quickly in class today. That's why, and I knew I had posted a video, but I wanted to just post another video, maybe visualizing a little bit more, and hopefully explaining it to you a little bit better, so you feel confident about the quiz next class. All right, so Godspeed.